Okay, 30 in itself is great. Alright. So for 30, they give us this rational function, and we don't know k, and they ask us to find k so that the limit exists, and then to actually find the limit. Now, in order for that limit to exist, again, we need that left hand and the right hand to be approaching the same thing. And most likely, if it's this factoring problem, we can probably factor it and get it to cancel out one of our factors, so that way we have just a hole there, and then we have the limit exists at that point. So for A, they asked us to check as x approaches 3, and if you try putting 3 in, you get 0 in the denominator, which, as you can see when we factor it, you can see that that ends up being one of our factors. So we simply needed this top to factor into something where we would have a factor of x minus 3. So same idea over here with B, except now it's approaching -1. And again, we can see that our denominator here, let me write that a little bit bigger, factor into x minus 3, x plus 1. So if I take -1 and substitute it in, I'm going to get 0 in the denominator. Again, if we can get the top to factor into something that has a factor of x plus 1, we can reduce those and then have just that hole there. So that's what we're attempting here. So again, my denominator is x minus 3, and on top I want x plus 1 and then some other factor here. Okay, so this is really just kind of using your noggin to figure out what our factors will be. I know that I have to have 2x if my other factor is x plus 1, so that will multiply to get into 2x. So at this point, I'm just going to go ahead and multiply out what I do have so far. So I have 2x squared plus 2x. And I don't know what this is going to be, and I don't know what this is going to be. All right? Now, I need it to add to give me just 1x. So if I currently have 2x, in order for it to simplify it out to just 1x, I need to have a negative x. Oh, no! Did I put plus x? Okay, so now that we see that, let's see what we actually get. Okay, do you guys agree that should be negative x? Okay, awesome. All right, so then what do I need to have here so that it gives me a negative x? What does this have to be? -1. Okay, so let's just double check. 2x squared plus 2x minus x minus 1. And that means our k value then would be -1. Do you guys agree with that? I heard a few yeses. Okay, awesome. All right, so now that k is -1, let's take a look at what that changes for us. Okay, so we have then, this is going to be 2x minus 1 times x plus 1 over x minus 3, x plus 1. Okay, so k being -1, so we want to take the limit as x approaches -1. Again, like we said, these reduce, so then we have the limit as x approaches -1 of 2x minus 1 over x minus 3. And when we do direct substitution, remember, once you do direct substitution, don't write your limit anymore. We're actually evaluating it. So I get 2 times -1 minus 1 over -1 minus 3. So -2, -1, -3 over -4. Positive 3/4. Do you guys agree with that? Yeah. Awesome. Okay. So positive 3/4. I'll make note of that. Yes, stop.
I was wondering if there's another way to approach this question, because I kind of did it differently, but I did get the same answer. I just don't know if it's
So what did you end up doing?
So for I guess for A, or for B, I plugged in -1 into the function, and I ended up getting 1 plus k over 0, and I found k so that it's 0 over 0, so that you get an intermediate form and it makes you factor. But I don't know if that's allowed if you're going to assume that it's 0 over 0.
Let me look into it more. I don't want to give you an answer and then it'd be wrong. So let me look into it more and then I'll get back to you on that. But I like that thinking there. So you substitute in to get that indeterminate form so then you have
So that you have to factor.
Gotcha.
For the quiz though,
Yeah.
do you mind if I would you rather have you this one?
I'd say stick to this for now just in case because I don't want to say do that and then it ends up yeah. Alright, other questions with that 30B? Sorry for that mistake. So in 30A, same idea as what we did here. We needed to add to the x, and so when we multiply out, we know again it has to be 2x here. And now instead of having the factor of x plus 1, we want to reduce it with our factor of x minus. So now when I multiply this out, I get 2x squared minus 6x, and then I need to figure out our last two terms. And so for it to add to be positive x, if I have negative 6x, I need plus 7x, which indicates this will be positive. So, and then same idea from there. Okay, questions with 30, A or B? Let's take a look at 36. Alright, so 26, we have one of our square roots. Now notice this is as x approaches negative infinity. Okay, so our end behavior models are only when we're looking at the ends, so that's x approaching positive or negative infinity. So here we have the limit as x approaches negative infinity of the square root of 2x squared plus 1 over 3x minus 5. And again, anytime we're taking the square root of an even power, this term is going to give us, here's another mistake. I already see it. Okay, so our end behavior model here. The term that controls the top is going to be square root of 2 times x inside an absolute value, because remember, square root of x squared is an absolute value. Now technically we know the square root of 2 is a positive value, so you could have written that out front, that's fine. Alright, and then what controls the bottom is 3x. Alright, so now as we can see, this is going to be balanced, so that means we just simply take our coefficients. So we know that our asymptotes are going to be square root of 2 over 3, but I need to know, is it the positive or is it the negative? Because we have those two different horizontal asymptotes. So if I take negative infinity and substitute in, on top I end up getting negative infinity put in, it's going to be positive on top, negative to the bottom, so our answer should be negative root 2 over 3. Are we good with that? Okay. Alright, so I just want to touch base on this again because I feel like this is a type of limit you didn't deal with a whole lot last year. So again, anytime that we're looking at our end behavior model, that is when we're having x approach positive infinity. If our degrees are the same, we know that we just take our coefficients. If it's top heavy, we know it's going to be a DME where you have to investigate whether it's positive or negative infinity. And we can see an example there with number 24 here. If I look at what controls the top is x cubed, what controls the bottom is 2x squared. So my end behavior model is going to be x cubed over 2x squared, which gives us 1/2 x. So the ends act the same way as the ends of our 1/2 x graph. So as x approaches infinity for my 1/2 x graph, my end would be approaching infinity as well. So top heavy, we look at our end behavior model to know what the ends are doing. And then bottom heavy, that's easy, that's just here. The only tricky thing is when we deal with our square roots here, make sure you don't forget absolute value of that. And then you have to check the positive. Yes.
But there's not, how do you get find the raise negative?
So what I'm doing is I'm taking the negative infinity, because I know that I have two horizontal asymptotes. One of them is at positive 2, or positive root 2 over 3, the other one's at negative. So I need to know which one is on which side. So I'm just simply taking my negative infinity, that sign, the negative, and substituting it. So on the far left side, it's going to be large negative numbers. So if I take a negative number, put it in, that gives me a positive on top. Negative number on the bottom will give me a negative. So overall. Does that make sense? All right, and then let's take a look at 16. So 16, there was a mistake on this. It should have been as x approaches negative 4. I think yours said positive 4. So this type of graph, absolute value of x over x, is that graph where we have that jump. And this is at A1, this is at -1. So this has just simply been shifted to the left for us. So you can think of your graph here, and then do your limit that way, or you can just simply take small numbers and substitute it. So if we think of our graph, we're looking at x approaching -4 from the left. That's going to be the -1. If we think of it in terms of just numbers, so we have, let's say, so we're going -4 from the left, so let's go really close to it, -4.1. So I'm just going to take -4.1, put it into my expression and see what I get. So the limit is x approaches -4.1. Absolute x plus 4, x plus 2. So -4.1. On top, that's going to give me an overall positive. On the bottom, that's going to give me negative. We know our options are either positive one or -1, so that's going to give me that -1. You could actually substitute the numbers, and that'll simplify down to -1 as well. So again, I think yours it said approaching +4. If it asks for an approaching +4, then you just do direct substitution, right? So always try direct substitution first. Your direct substitutions would yield an issue. So if it was approaching +4, and just put in 4 and we get 80 over 80, which is fine. Okay, questions of 16. All right, so what we have going on today is your limit quiz. It's just a short 10-minute limit quiz. I want to kind of recap some things with our limits homework before we do that, just to refresh our memories. It's been a few days since this. And then we're going to talk about continuity and intermediate value theorem. Now, continuity, everyone has dealt with, even back in Algebra 2, but intermediate value theorem, has anyone dealt with that before? So if you cover that if you're not on it. No? Okay, that's perfectly fine. So intermediate value theorem is one of our first kind of calculus topics, and it's an existence theorem. So it tells us that a certain type of value exists given certain circumstances. Okay, but before we dive into our quiz, I want to just go and kind of refresh our memories with a few things. So we talked about limits approaching infinity. Remember, make sure you use proper notation. If you're going to do a bunch of work, just off to the side, write work and do your work. Make sure it's still nice, neat, and organized. In calculus, even on the AP exam, they're pretty picky about this. If you are not neat and organized with your work and they can't find the answer, you just won't get credit. So make sure you're neat and organized with your work. Every time that you're manipulating the limit, you still need to write the limit. But once you do direct substitution or you apply one of these rules about limits, such as our special trig limits, you no longer need to write limit. You just actually go, you drop the limit actually. Let's see. For a problem like number 14, make sure that you are checking each of the conditions here. So you check your left-hand limit, check your right-hand limit, and then the overall limit. And when it comes to piecewise functions, I think we talked about this last class, AP is very picky with this. We have to specify which piece of the piecewise we're working with. So we say the limit is x approaches 3 from the left of f of x, and then you need to actually specify that that is the branch 6x minus 1. Then you can go ahead and evaluate your limit. So check the left, check the right, state whether or not they're equal, and then you can state whether or not your limit exists. All right. We talked about how we can factor, conjugates. Remember, please, 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 always first check to see if you can do direct substitution before trying to. All right. That's it. Any lingering questions before we go ahead and start? Go ahead and just take a couple minutes to look through any last minute stuff we want to look at. We'll kind of clear off the board up here, and then we'll get going on the quiz. Yeah. Yes. Yeah. So this one, there's. And so what this does is so I know oh yeah, so that should have said and then that was it. Yep. Okay, just a quick recap too. We did our trig limits last time, so limit as x equals 0 sin x over x is 1, and our 1 minus cosine x over 1. Here. Now, what if I start throwing in stuff here? Oh, look at that, so nice and easy. How about that? Good. Just want to make sure. Okay, so in calculus, you'll notice that everything is pretty much has some type of time limit for assessments. Now, this quiz is a little different than our future quizzes. This is just a very short quiz on limits. Our future quizzes are going to be more AP style in that it has cumulative material. And there'll be calculator, non-calculator portions, multiple choice, response. But this is just kind of your old-fashioned, quick, short little quiz on limits. Now, it is only 10 minutes, so I'm going to pass it out to you upside down. We're all going to wait till we get it so that no one complains that somebody got 30 seconds more than somebody else. And when I say go, then we'll flip it over and start. Okay? Now, you'll probably finish it long before the 10 minutes. But if you do, just flip it over and draw me a picture on the back. And then I'll collect it from the front. Normally, I'll have you turn it in over on the bookshelf, but again, since it's just such a short quiz, I'll then call time and then have you pass it forward, and then we'll, I'll take it from there. Okay. So again, keep it upside down. You guys so excited. Good. Don't start yet. Just a reminder, use proper notation. Keep writing limit until you evaluate the limit. Put equal signs when things are equal. Does everyone have a quiz? Okay, Neymar. Good set. Go. Okay, so unit 1, day 3, we're doing continuity. And IVT, intermediate value pair. Now, last class I talked about how AP does not allow very many abbreviations at all. IVT is one of the abbreviations you can use. Woo! Instead of writing intermediate. Okay, so I had you discuss with your shorter partner what you remember about continuity. So volunteer up some information they recall from the previous years of glorious math. Yes. Ashley. No, Lauren! Who goes this way? You. Timmy boy, you. All right, Lauren.
There's removable jump and continuous.
Ooh, good. So we've got 3 types of discontinuities. We've got removable, jump, and infinite. Good. What else do you remember about continuity? What does it mean to be continuous?
So right,
There's no holes in the function. What was it when you first learned continuity? I think back in algebra 2. What would they tell you to do to decide if it's continuous? Trace it with your pencil, right? If you could trace it and didn't have to lift up your pencil, it's continuous. Now we're going to go with a more mathy definition today. But how does continuity compare to a limit existing? Talk to your shorter partner real quick. What's the difference between a function being continuous at a point and a limit existing at a point? We're going to talk to your shorter partner Okay, go ahead and bring it back up front. Anybody feel confident enough that they want to share? What's kind of the big difference between the two? Yes, Sarah.
You can have like removable discontinuity, but you can still have.
Good. So would you guys agree that for a limit to exist, that point doesn't have to be there, the function doesn't have to be defined there, but for it to be continuous, it does need to define and be the same on either side, right? Are we good with that? Okay, so let's go ahead and formally write this stuff out. A function is continuous if and only if. Ooh, does that bring me back to geometry? What kind of statement is it if and only if statement? Biconditional, good. Alright, a function is continuous if and only if the following holds true. And I'm going to write it as 3 separate things. What? Oh, sorry, I should have said is continuous. Oh, man. Right here. Alright, it is continuous at C. So, like, at a point C. I'm sorry, this is continuous at a point. So it's continuous at a point if and only if f of C exists. So the function is defined at that point. The limit as x approaches C of f of x exists. So the function is defined at that point, the limit exists at that point. And then the most important piece is that the limit as x approaches C of f of x equals f of C. So 1 must be true, 2 must be true, and the third step is that 1 is true. That really bothers me, that that's not in there. Okay, a function is continuous if and only if all 3 of these hold true. If it fails any of these 3, it's not continuous at that point. Now, we've talked about how a function is continuous just in general. So like back in algebra 2, it's saying, is this function continuous? What we're talking about is if it's continuous on that interval that you're seeing. Sometimes they would ask you to write the intervals for which it's continuous. Sometimes you'll see where it says, is the function continuous on its domain? And what that means is where the x values are defined, is it continuous for that place? So just make sure you're kind of looking for that terminology. So here we're talking about at a specific point. If it's continuous at all the points on its domain, then we say it's continuous on its domain. But for right now, we're just talking about at that particular point. Okay, now step 2 has a little more to it than just limit existing. Because we know from previous classes that in order for the limit to exist, that means that the left-hand limit, the limit as x approaches C from the left, must equal the right-hand limit. So sometimes you're given a nice graph and it gives all your information there, and you don't have to do left-hand limit, right-hand limit. But there are times in which maybe it's a piecewise function in which you have to check the left-hand limit, check the right-hand limit, and check the test. So make sure that you don't skimp on any of the work. Make sure you have each of these 3 pieces. Okay, any questions on just putting these pieces? Okay, let's go ahead and dive into an example. Oh, nope, I take it back. Let's draw out those types of discontinuities that we just talked about. All right, so we have 3 types of discontinuities. And again, we're talking about being a continuous type of All right, so the first one we have is called a removable discontinuity. So that's going to be your pole. So we have that pole, in our layman's terms, if I were to trace it, I'd have to put my pencil across it. When we're looking at an equation in which there is a removable discontinuity, what does that mean? What does that mean has happened to our equation or our expression if there's a pole? Yeah, so we have a set of factors cancels for each system. So I'm just going to go through an example, x plus 1 is x minus 2 over x plus 1 times x minus 4. So here we have these reduced, so there is a pole at x equal to -1. Alright, so we have removable discontinuity. We also have our jump discontinuities. And most often this is represented in a piecewise function. Not always the case, as we saw with the absolute value of x over x, that gives us a jump as well. But most likely it's going to be at some type of piecewise function. Okay, so we have this jump here. You could have one of these filled in or not, doesn't really matter. So this is again usually piecewise functions. And just because it's piecewise doesn't mean that it is going to have a jump. But normally if we have a jump, it's often for piecewise functions. I'm also going to include the absolute value of x over x. Okay, and then our last one, we have our infinite discontinuities. Okay, so our infinite discontinuity, we have some type of asymptote. Okay, so this is vertical asymptotes. How do we know if there's a vertical asymptote in the graph? How does that represent itself? We said that holes is when a factor reduces. How do we know if there's a vertical asymptote? Rational function, what specifically about the rational function? Factor on the bottom. Good. So it's where our denominator equals 0. Okay, so let's just go and say 5 over x minus 2. We have a vertical asymptote at x equal to 0. So that would be where our discontinuity is. Okay. Any questions with that so far? Okay. Let's go and take a look at function x squared minus 9 over x minus 3. Continuous at x equals 3. because this function includes an x. Anytime you see justify, show your work, or really anytime it's a free response type problem, you're going to want to make sure you check the 3 conditions. Once it has failed one of the 3 conditions, then you're good, you can stop. But make sure you actually check each of the 3 conditions and show all your work proper notation for it. I guess for multiple choice, we're not looking at your work. AP exam doesn't look at your work, so you do whatever work you need to for it. A free response, you do need to make sure you're clear, you're organized, and that you label everything for you. Okay. So again, let's check our 3 conditions. First of all, we've got to have the f of 3 exists. So let's go ahead and check out what is f of 3. Alright, well if I try to take 3 and plug it in right now, then I'm going to end up getting 0 in our denominator, which is an issue. What can I do to investigate it further? So we know that if we take 3 and put it in, that's going to be a 0 right away. We know there's an issue that is continuity. But if we wanted to look at the limit, what more can I do to this problem to investigate it further, see what's happening there? What's that? Yeah, so we want to go ahead and factor that numerator in. Okay, so now if we try to take 3, put it in, we end up getting 3 squared minus 9, 3 minus 8, which gives us that 0, 0. So the function here is undefined. Right away we can go ahead and say f of x is not continuous at x equal to 3. Right. So right away we know it's not continuous at x equal to 3. To investigate it further and figure out what type of discontinuity, we can go ahead and factor it and simplify from there. Now, if they don't ask for what type of discontinuity, you don't have to state it. But let's go ahead because it's good for us. Let's go ahead and say what kind. So let's investigate a little bit further. If I factor the top, I get x plus 3 times x minus 3 over x minus 3. Yippee-ki-yay, these reduce. So what type of discontinuity is this? Good. Removable. Good. Which is what you meant, right? Alright, so what we have is a removable discontinuity. And we want to state where it's okay, discontinuity at x. Okay. Now again, if they don't ask for that certain type, you don't have to specify what kind. But here it failed the very first condition. Our function is not defined at 3. So if the point doesn't even exist there, it's not possible for it to be continuous there. Okay. So let's go ahead and see how can we rewrite this. How can we rewrite f of x so it is continuous at that point? So how can we rewrite f of x so it is continuous at x equal to 3? Alright, so we know that there's some type of hole there. Would you guys agree that it's continuous everywhere else though? Once we take a look at this. Okay. Now, I want to make sure we understand, even though this reduces down to x plus 3, this graph and this graph are not the same. They look very, very, very similar. They look exactly the same, except at the point x equal to 3, this is going to have a hole, this is not. But we manipulate this, we simplify and reduce it down, so we do have an idea of what that graph looks like. But I want to make sure we understand they are not the same graph. They're extremely close, but not quite. Okay. So anyway, how can we rewrite f of x so it is continuous at 3? Well, if we've got that hole there, how do we fill in a hole? If you've got a hole in the ground, how do you fill in a hole? You just fill in the dirt, right? If we've got a hole in the grass, how do we fill in a hole? Fill in the hole with a dot. We want that function to actually be defined there. So we've got to figure out, so what we have happening is that there's some type of hole at 3. This is not what the graph looks like. That's kind of like that. So we just need to figure out what is that actual function value. If I can go ahead and define that, say f of 3 equals whatever number this is, then I filled in the hole, right? How do we figure out what that value is? Good, good. So our simplified form. All right, so we have the simplified form, and I'm going to rewrite this as x plus 3 for x not equal to. Yeah, okay. So I'm rewriting my function saying, hey, this is my graph for everywhere except f3, okay? So what Chelsea said is, we'll just take your simplified form, take 3 and substitute in, that tells us the height at which that hole occurs, and that's the height at which we want to fill in. Okay, so let's do f of 3. 3 plus 3, which equals 6. Alright, so now I have my function, and I have the hole. Let's go ahead and compile it together just in a piecewise function. So let's rewrite f of x as a piecewise function. We can go ahead and keep the original function x squared minus 9 over, what was it, x minus, yeah. And we'll specify when that occurs. And then we also have the single value of 6 when x equals 3. Okay, so we know at x equal to 3, we want the function to be 6. And then for everything else, we want the function to be just the original function as it is. Alright, so my notation here, it's everything but 3, so I'm just going to say for x. Okay, so my function as is for everything but 3, but since that's where that value is, I'm going to specify exactly what that value is at 3. Does that make sense? We're filling in that hole just with that single point omitter. Okay. Questions with that? All right. Let's go and take a look at another type of problem you might encounter with our problem. So let's say they give us f of x equals ax squared. This is a piecewise function here. Ax squared plus 2 for x less than -1. And the function x is x greater than or equal to -1. So our function given to us is a piecewise function, ax squared plus 2 for x is less than -1. And x when x is greater than or equal to Okay. And they ask you what value of a will make f of x continuous at x equals 1. Sometimes they might first ask you if the function is continuous, and then they'll ask you what value will make it continuous. So here they've given us a quadratic, we have that linear, we need to make sure that it's continuous. Most likely, it was some type of jump or some sort like that. So we need to make sure that these two graphs match up. So at -1, they need to have the same value in order for them to match up. So let's go ahead and just go through the pieces of continuity. First of all, again, our function needs to be defined. So do we have f of -1? Why, yes we do. That's simply -1, put in for x. Oh, just okay. So again, we can see it's defined. I'm just taking that value substitute in, so I actually have the function defined. And then our next piece is that the limit needs to exist. So what we want is for the limit from the left, limit as x approaches -1 from the left, to be the same as the limit from the right. Because I need my overall limit to exist. In order for my overall limit to exist, I need the left and the right to be the same. So let's talk about our piecewise. Top or bottom, which one is my left piece of the graph? Good. So that's going to be the left side. This is my right side. Okay, so I basically need this left hand to equal up with the right hand. Okay, so what I want is for this limit to exist. So that would be the limit as x approaches -1 from the left. And we said that is the function ax squared plus 2. And I need that to equal, again, we want these to be equal, right? I need that to equal the right-handed limit, the limit as x approaches -1 from the right. And again, from the right is just x. Now, as you're going through, I do want to see the notation here of setting up your limit symbols. Okay, well now we know how to actually evaluate limits, so let's go ahead and substitute in our -1. So if I take -1 and put it in, we get a times -1 squared plus 2. So I'm actually evaluating my limit by doing direct substitution. And then evaluate your limit on the right side. Take a -1, put it in. And now we have an equation that we can use to solve that a value. So again, I want my left-hand limit to equal my right-hand limit. I look at my piecewise function to set that up to which piece I'm working with. Then actually do your direct substitution with your x values. So you have an equation where it's just a and some numbers. Questions with that so far? Okay, so let's just go to solve. So we get a plus 2 equals -1. And what do we get for a? -3. Okay. Now, sometimes they'll ask you then to actually go ahead and evaluate the limit. In that case, you just take a, put it back in, and then actually keep your left and right. Questions with that? Okay, so you'll notice on your homework tonight you have some way to solve. It might have said K, if you remember everything. I think K is more common. So again, make sure you check left hand, right hand, find, we'll set up that equation where you take the direct substitution, put it in, and solve for that unknown value. And if it asks you to actually find limit, make sure you go back and actually do it. Okay, let's go and take a look at a little more information with continuous functions, and we'll talk about it anyway. All right, so some functions are always continuous. Some functions are always continuous. Polynomials. Absolute value. And any odd root function. So like cube root, fifth root, cube root of x. Now, a couple more things about continuity. If f of x and g of x are continuous at c, so if we've got two functions that are continuous at a particular point, at x equals c, then we have certain properties that hold true, similar to like our limit laws. So then we know that if I have a coefficient times our function, that's going to also be continuous. If I have my function raised up to, that's also going to be continuous. If I have the two functions added together or subtracted, that's still continuous. If I have them multiplied together, that's still continuous. If I have them divided, as long as the denominator is not equal to 0, then that is also continuous. So if our original two functions are continuous, then pretty much we can apply our arithmetic rules to it. All of these are also continuous. Which, if you think about it just with a polynomial, we have the function x squared is continuous as well as x. So the function x squared plus x is continuous. The function 5x squared, 5x squared times x is continuous. Okay. And then we also deal a little bit with compositions. All right, so another note here is if g is continuous, that's c. G is continuous at x equal to c. And f is continuous at g of c. So So we're doing composition here. So we take C, put it into our G function if it's continuous at that point. Take that, put it into our F function. Then we have that composition is continuous. Okay. So if G is continuous at C, we take that, and F is continuous at that. And we know that composition is continuous. And F of G of X is continuous at X. So just real quick, an example with that. Let's say that we have h of x is the absolute value of 5x squared plus 1. Oops, absolute value. And we're looking at x equal to 3. So here we have a composition of functions. We've got a quadratic and an absolute value. So if 3 is continuous for this piece, and if we take 3 and put it in, what do we get real quick?
46. Plus 1.
Oh, I was doing 5 times there. I'm like, oh my gosh, I'm only getting 16, guys. Okay, sorry, 46, good. So we have then, if we take 3, put it in, it's continuous at that, right? We get 46, and then absolute value at that new point, absolute value of 46 is also continuous. So really all it's saying is that the composition is continuous as long as this substituted in the new value is continuous. Okay, so it's not as crazy as we think. We're often dealing with composition of functions. But again, if I take this and substitute it into my function, and that's continuous, take that new value and put it into the next function, that's continuous, then the composition is continuous. Okay, so again, these are kind of like the limit laws where you often use them without even thinking about it, but it's just some more information. All right, questions with that? Real quick, I want to go ahead and just state what the intermediate value theorem is. We'll do more with it maybe next time, maybe not. So real quick, I want to state what the intermediate value theorem is, and then we're going to do more with it. So on your homework, I won't have you do the intermediate value theorem piece, but I want to make sure we at least touch on it. Here we go. Intermediate value theorem. Alright, so the intermediate value theorem, or IVT, says the following. If f is continuous, on the closed interval from A to B, f is continuous on the closed interval A to B, and f of A does not equal f of B. So those endpoints are not at the same height. Alright, so if f is continuous in that closed interval, the endpoints are not at the same height. If k is any number between f of A and f of B, okay, so we've got two different y heights. K is some value between those two different y heights. Then there exists at least one number, C, in the open interval from A to B, such that f of C is the following. I know, it's a long one. It's a long one. And we'll talk about it next class, what we're dealing with here. Actually, we'll leave it as a cliffhanger. Oh, we still have 2 minutes. We'll leave it as a cliffhanger. So, let me explain to you what the idea is. Pretty much what we have happening is 2 different y heights. And it says, if I've got a y in between those, and as long as the function is continuous, if it hits all those y's in between, then that must occur between the x values. So, for example, you were probably, what, like 20 inches when you were born? You guys agree with that? Somewhere around that? And now you're probably more like 65 inches, maybe like a few inches or something. Is your height continuous? From when you were born to now, did you hit every single height in between there? Yeah, so you didn't jump around in heights, right? So from birth to now, you probably at some point were like 3 feet 2 inches, right? So we have 2 different heights, starting point and an ending point. And basically what this is saying is that you must have hit every single height in between there at some point between 0 years old and 17 years old. So we'll talk about that more next class. Remember, next class is your test, right? So the review worksheets are up on Blackboard. It's just a bunch of extra practice. So for algebra review, there's logs, we've got trig, all kinds of stuff. This is prerequisite skills. So this homework, I did it say it's due next class? Is that extra? So this homework comes in next class. The intermediate value here, just skip those ones, and then it is for grade, yes. So class is a grade. So in your grades, there's just homework, and then there's like quiz and tests and the assessment. So just over any prerequisite knowledge. So you look at the worksheets on Blackboard. The key for the summer assignment also is up there. So look at it, see what you need to do to prepare for that. I'm not collecting those I'm not collecting those review worksheets. It's just there for you to do practice.